Okay, what we're going to look at now is how we can compare the rate of hydrolysis of different halogenoalkanes. So we've got three here. They've all got two carbons in the chain: chloroethane, bromoethane, iodoethane. And when we do hydrolysis, they all make ethanol. And we want to see, out of the three, put them in order of rate of how quickly this happens. Okay? So let's have a look how we can do that. When you're comparing different rates of reaction, it's important that you're making a fair comparison so that you've got a fair test. So certain things then we've got to keep the same. We've got to have equal moles of the halogenoalkanes. Okay? It would be an unfair comparison if we had more of one than the other, because obviously the one you have more of would take longer to completely hydrolyse. So we have equal moles of the three things that we're comparing in this case. And we're keeping the chain length the same, so they're all something ethane, so chloroethane, bromoethane, iodoethane. Okay? I'm not having one that's got three carbons rather than two, so I'm keeping that factor the same, keeping that one constant. Rate is greatly affected by temperature. Okay? So we don't want to change the temperature as well, we want to keep that the same. And the easiest way to do that in this type of experiment is to have a water bath. So you can use an electronic water bath. And that will keep the temperature constant throughout the reaction. Now, we want to make sure that when they react, they're all at the same temperature. So the silver nitrate that we're going to use, the halogenoalkane, we're going to be heated separately in the water bath in separate test tubes. And then once they both get to the same temperature, so about 50 degrees, we're then going to mix them together. Okay? So we're not having one that's at 50 degrees and the other one out at room temperature or whatever temperature and then mixing it. They're both at 50 degrees before we mix it. Okay? Right. So, how does the process work? Okay, so into our test tube, we've got the halogenoalkane, aqueous silver nitrate and ethanol. Okay? So if you notice this time it's hydrolysis, but we're not using sodium hydroxide. And the reason for that is that the sodium hydroxide would react to the silver nitrate and we don't want that to happen. So instead the nucleophile we're using is the water that's from the aqueous solution. Okay, that's our nucleophile. So it would react, in this case got an example with chloroethane, it reacts in the same way. It's a nucleophilic substitution. Okay, it comes in here, it replaces the chlorine to make chloride. You get H plus as well, because that's come off from the water. So you're making ethanol. Okay? But we're not using sodium hydroxide. We use ethanol here in this, nothing to do with this ethanol being produced, we use ethanol in this as a solution, as a solvent, sorry, because it dissolves the silver nitrate and the halogenoalkane. So they've got to be able to mix together. Otherwise they won't mix. Okay, and you'll get two in separate layers. So for them to be able to react, they've got to be able to mix together. So we need something they both dissolve in, and that's why we use ethanol. So we've got the ethanol to make sure everything dissolves and mixes together so it can react. We've got the silver nitrate, because the silver nitrate is important because it's going to react with the halide ion produced. In this case, the chloride, but it could be the bromide or the iodide. Okay, it's aqueous because we need the water in there, because the water is our nucleophile. And we need the halogenoalkane which we're testing. Okay. So once we've got our solutions in there, we've got our silver nitrates, and we've got our halogenoalkane and ethanol, all at 50 degrees. We mix them together, okay, and we time how long it takes for a precipitate to form. So in each reaction a halide ion will be formed, because in the substitution reaction the halogens are removed to make a halide ion, and in each case, because there's silver nitrate in there, it will react to the silver ion to make a precipitate. Okay, so it's a very similar reaction to when we're identifying them. This time we're timing how long it takes it to form a precipitate, and depending on how long it takes we can we can work out the rate of reaction. So the longer it takes, the slower the rate of reaction. The quicker it forms to precipitate, the faster the rate of reaction. Okay, so these would be the three, in this case, the three precipitates that we'll see form. So if you've got all those factors that we looked at before, we've got all those factors constant, so we're only comparing the difference having different halogens, then we can look at what affects the rate. Okay, and the thing that affects the rate of reaction is the bond enthalpy. Okay, the bond enthalpy is how strong a bond is. And we find that the stronger the bond is between the carbon and the halogen, the slower the reaction. And that makes sense because it's the halogen that's got to leave the molecule, and it can't leave until that bond between the carbon and the halogen is broken. So if that bond is not broken, the reaction hasn't happened yet. So the stronger the bond, the slower the reaction. So which bonds are stronger? The smaller, more electronegative halogens form the stronger bonds. So they have a slower rate of reaction. So at the top of the group, group 7, you've got fluorine. We don't see too many of those, fluorohydrocarbons, but they do exist. So they have very strong bonds. Okay, the fluorine is very small, very electronegative. It's got a very strong covalent bond to the carbon. So that's got a very slow rate of reaction. So the hydrolysis process takes a long time. Then we've got the chloroethane, then the bromo, then the iodine. So by the time we get down here, the iodine is a much bigger atom. Okay, its electronegativity is very small compared to the others, and that means that bond's much weaker. So it's easier to break, which means the substitution reaction is much quicker. It's easier to remove the iodine from the molecule and replace it with an OH. And there you can see that as we go, basically we're going down group 7, the rate is getting faster because the bond is getting weaker between the carbon and the halogen.